Okay, so this talk came about because Scott and I were driving in the car together, and we were talking about. I was talking about this little program that I wrote to compute Kazhdan Lusztig polynomials on a computer, and Scott was interested to know how exactly that is done. And so here we are. We're going to explain what Kazhdan Lusztig polynomials are and how you can compute them. And well, as the name says, Kazhdan Lusztig polynomials are originally due to Kazhdan and Lusztig. So most of the material that I'm going to present is due to them, but the entire notational setup and the algorithm are due to Wolfgang's algorithm. So most of the stuff that I'm going to talk about follows Kazhdan Lusztig. And maybe a little bit of motivation why you might be interested in Kazhdan Lusztig polynomials. Well, one valid reason is that they control basically all of the representation theory of complex simple Lie algebras. So if you have G simple Lie algebra, by group W then what one usually studies in the representation theory of this Lie algebra is one looks at VGG category O in its principal block. So we have O0 in the principal block. Of VGG category O. And in there, we have simple objects indexed by the while group. Simple G modules in the principal block are in projection with the while group, and we write x goes to Lx. And the way these simple objects are constructed, each of them arises as the unique simple head of a Verma module. Okay? So you also have a Verma module which surjects onto the simple module, and it is defined as the induction from Borel subalgebra to the entire Lie algebra. So you take the universal M-looking algebra of G, you tensor it over the universal M-looking algebra of Borel subalgebra with the one-dimensional representation, and this one-dimensional representation should have weight x led to minus rho, where rho is the half sum of all positive roots. The whole point being the Verma modules are things we understand rather well. We know how to construct them and we know what they look like. The simple modules is what we would like to get at. So the important questions here are, for example, what are the composition multiplicities of the simple modules inside the Verma modules? And what are the dimensions of the X spaces between them? So what is dimension of X I in category O between delta X and Ly? And so this is not going to be the main topic of this talk, but both of these questions have answers in terms of Kazhdan Lusztig polynomials, and that motivates why we should be interested in how to compute these polynomials. And the answers are that if you want to know the composition multiplicity of a given simple module in a Verma module, this is going to be an inverse Kazhdan Lusztig polynomial corresponding to x, y evaluated at 1. So this is inverse Kazhdan Lusztig polynomial. And if you take all of these x groups that we're looking at above and we write them into one polynomial, so take the sum of all the dimensions of the x I between a given Verma module delta x and the simple module Ly, you multiply each of those with some variable, with some power of a variable v, then this turns out to be a Kazhdan Lusztig polynomial. So, yeah, the point of this talk is to tell you what exactly these are and how you can compute them explicitly for a given Weil group or another Foster group. And I'll start with some notational setup for Foster groups and Hecke algebras. So, I assume that most of you are familiar with the concept of a Foster group. Just to recall, so we take WS, a Foster system, and that means that W is going to be a group which has a generating set S, and there are relations of the following form. So first we have S squared is equal to the identity, so it's generated by a set of involutions. And then secondly, for every pair of these generating involutions, we're going to have a braid relation. So if we take ST and we raise it to some fixed power MST, this is part of the information of the Foster system, then this is the same as taking TS and raising it to the same power. ST. Okay, and we have these relations for certain MST, which should be greater or equal to, but it might also be infinity. So the product of two of these involutions might have infinite order. Right, so this is a Foster group, and the easiest examples that you can think of are, for example, the dihedral group of order 2n, which is generated by two reflections as T, subject to the relations S squared equals T squared equals E, and ST to the n as TS to the n. Or you can take a symmetric group acting on n points, and this is generated by n-1 simple reflections, so it's 1 up to Sn-1, subject to the relations of all the Si squared to the identity that Si and Sj commute if the indices are distant, so that means that the absolute value of I minus j should be greater than 1, and finally you get this braid relation which says that Si plus 1 times Si is the same as what you get when you reverse the order, so you get Si plus 1 times Si times Si plus 1. Sorry, I wrote this incorrectly. So this relation should be written as St to the MST is equal to the identity, but that amounts to the same as saying that ST, STS, MST copies, it's the same as T, ST, ST, MST copies. So in this case, we get that MST for these two reflections is precisely 3. Okay. All right. So these are examples of Foster groups, but you can also think of affine Weil groups, for example. These give like a nice family of infinite Foster groups, whereas these examples are just finite. Okay, so also you can think of the Weil group of any complex equilibrium, the example was coming from earlier. Now, given any such Foster system, you can define a Hecke algebra, as follows. Just can denote it by H, but in principle it depends on the Coxeter system, so we can also write H lower WS is an algebra over an integer Laurent polynomial ring with generators that we denote by HS, and they're indexed by the simple reflections of our Coxeter system, and then we have two types of relations. First, there's a quadratic relation, which says that we should have HS plus V times HS minus V inverse to 0 for all S. So this is the quadratic relations. And secondly, we should have that if we take the product of HS, HT, HS, and we keep going until we have MST terms in this product, then this should be the same as HT, HS, HT. Again, we keep going until we have MST terms in the product. And this is called the wave relations. Right? This is the definition of the Heck algebra. And there are two simple observations that I want to make about this definition. First of all, if you take an element of your Coxeter group and you write on a reduced expression, so you write W plus S1 up to Sn, and reduced expression means you write it as a product of these simple reflections in such a way that it's not possible to write it in any shorter way. So with reduced expression W equals S1 up to Sn, then the element HW, which you write as H S1 up to H Sn W, this does not depend on the choice of the expression. Okay, so I don't want to write down a proof for this. It's a fairly standard fact. Whenever you have these great relations and you multiply things in the order of a reduced expression, the thing that you end up with doesn't depend on the chosen expression. Okay, there is a little work to do when you want to prove this, but it's not too hard. It's sort of just looking at Coxeter groups really and how you can pass from one minimal reduced expression to another. The second fact that we have is that if we multiply HS with HS plus V minus V inverse, then we end up with 1. So this is an easy exercise using the quadratic relation. And the same if you multiply them the other way around, because these two compute with one another. So in particular, all the HS are invertible, and so all the HW are also invertible. W and W, and so the set HW with W and W actually forms the basis for the Heck algebra of the Laurent polynomial ring, and we call it the standard basis. So now we're ready to talk about Kazhdan Lusztig polynomials.
may want to see what happens when b goes to 1. I mean,
Sorry?
you may want to see what happens when you specialize b to 1.
Oh, you mean the here W in this case? Or where?
Yeah, for the heck algebra.
Oh, sorry. Yes. If you right, if you look back at the relations that we get, the second relation, the break relation, doesn't depend on V. So you just end up with a break relation for the group, and the quadratic relation at V equal to 1. So this becomes sort of the third binomial formula. So you get h squared minus 1 is equal to 0. So h squared is equal to 1, which is the first relation for the Kopfler group. So the algebra that you end up with at V equal to 1 is just the group algebra of the Kopfler group. So you can think of the Hecker algebra as a kind of quantum deformation of the group algebra of the Kopfler group you started from. Thanks for pointing that out. Okay, so in order to talk about Kazhdan Lusztig polynomials, the most important piece of information to get the theory started is the so-called bar involution. Okay, so the Kazhdan Lusztig bar involution is the unique ring homomorphism of H. Ring homomorphism denoted by bar from H to H, such that if you apply bar to the variable v of the Laurent polynomial ring, you just get v inverse. And if you apply the bar involution to some hx, you get hx inverse inverted. Okay, and this makes sense because of what I said before, the hx, they're all inverted. Okay, so that's a unique ring homomorphism with these properties. It's denoted by bar. It's going to be an involution because it acts as an involution on the Laurent polynomial ring, and it acts as an involution on the basis. So this name makes sense. And I want to give you an example. An element that is self-dual with respect to this involution, so it's fixed. Namely, if you look at the element h underline s, which is just hs plus v, then we can compute the bar involution as follows. So we need to take, so s is its own inverse because s squared is equal to 1. So we need to take the inverse of hs. We've seen before that the inverse of hs is this here, hs plus v minus v inverse. So this is hs plus v minus v inverse. And then we need to apply the bar involution to v, which gives us the inverse. So we end up with just hs plus v, which is hs under n. So this is h under s. Okay, so this is one nice self-dual element. And what we'll be interested in is producing more self-dual elements of the Hecker algebra. And this is the main theorem which I want to prove, and the proof is also going to give us an algorithm for producing these elements. So this is essentially due to Kazhdan Lusztig, but in this formulation it's due to Wolfgang Zörgel. For all elements x of the Kopfler group, there is a unique element h underline x in h, such that h underline x is self-dual with respect to the bar involution, and furthermore, we want that these h underline x are sort of lower unit triangular with respect to the standard basis. So you can write h underline x as hx plus, and then we get certain things where we sum over elements y that are below x in the Gruber order of the Kazhdan group that we started from. And we get certain polynomials h, y, x times standard basis elements. Now this is not very surprising so far, but the sort of the key fact here that makes this theory so powerful is we can choose these polynomials in such a way that all of them are actually polynomials with constant term 0. So they're actual polynomials and not law polynomials. Okay? Right. And then, I mean, it's not a coincidence that I chose the same notation as notation that I chose in the introduction. These polynomials h, y, x are actually the Kazhdan Lusztig polynomials that we're looking for, and this self-dual basis is the Kazhdan Lusztig basis. It is a basis because of the unit triangularity. So it's the law of unit triangular with respect to the standard basis. So it's sort of just, I mean, you have an invertible change of basis matrix. So as I said, this here is the Kazhdan Lusztig basis, and these polynomials are the Kazhdan Lusztig polynomials. All right. So the existence part of the theorem, because that is going to be interesting for seeing how we can actually construct this basis. So we go through the proof of existence. And we do this by induction on the length of a minimally reduced expression for the Kazhdan group element x. Check the length of x, and the two first cases are already settled because the Kazhdan Lusztig basis element corresponding to E is certainly going to be the standard basis element HE. And in the preceding example, we have already seen that we have a self-dual element H underline S given by HS plus V. And here, the only coefficient on an element that is smaller than S is the coefficient on HE. So this here, technically, you should write this as V times HE. And here you see that this is actually a polynomial with a non-zero constant term. With constant term 0, which is what you want. Now, suppose that we take an element x with length of x at least 2, and then we can choose a simple reflection such that when we multiply from the right, say, the length of this element goes down. Okay. So we take S such that the length of xs is smaller than x. Okay, and now we need to look at what happens when we multiply something from the right with this hs. So there's two technical formulas, not really technical formulas, but we use two formulas which are very easy to compute. So for any y in w, we have that if you take hy and you multiply it with h underline s from the right, then there are basically two options. Either you get hys plus v times hy, and this happens if the length of ys is greater than the length of y, or you get hys plus v inverse times hy, and this happens in the opposite case, so if L of ys is less than the length of y. Okay, and now based on these computations, let's look at the element that we get when we take h underline xs, which we know exists by induction. Right? So this thing is shorter length of assumption. So we can multiply it by h underline s. And since the bar involution is a ring homomorphism, the product of two self-dual elements is again self-dual. So this thing is going to be self-dual. And furthermore, if you look at this product, h underline xs times h underline s, and you expand it in terms of the standard basis, then basically by construction, so there's going to be precisely like the term, the standard basis element hs is going to appear with coefficient 1 here. The standard basis element corresponding to x is going to appear with coefficient 1 here, and so you get hxs appearing with coefficient 1 on this side, and then you get a sum over things y, which are less than xs in the Gruber order, and certain polynomials, let's say p y times hy. And the important observation is that, so essentially all the polynomials appearing in the expansion of this here in terms of standard basis elements, except for the leading term for coefficients corresponding to xs, are going to be multiples of a polynomial by v. Okay, so polynomials with constant term 0. And since we multiply with h underline s, the worst thing that can possibly happen is we introduce one additional v inverse. Okay, so if you take a polynomial from here, you multiply it with the inverse, you still end up with a polynomial and a Laurent polynomial. So this means that all of these coefficients py are not Laurent polynomials, but actually polynomials without any v inverse in it. Okay. And now we can use this. Basically, we can use the fact that everything that appeared in the sum is less than xs, and so we can use the Kazhdan Lusztig basis elements that we've already constructed by induction to eliminate all the polynomials where we have a non-zero constant term, and we do this as follows. Define h underline x to be where we start from h underline xs times h underline s. But then, as I said, we take away everything that has a non-zero constant term in this expansion, y less than x s, and then we take these polynomials py, we evaluate at 0, that's precisely the constant term, and we take away h underline y, which we have computed before. And that's all we need to do, because, as I said, this eliminates all the non-zero constant terms, so now the result that we get is precisely in this shape. And furthermore, since we take a product of two self-dual same things, and we subtract something self-dual, the result is going to be self-dual. Okay, so this works existence. Basically, I just want to say, if you want to prove the uniqueness, one first shows that an element H of the Hecke algebra, which is self-dual, and also is a linear combination of standard basis elements in such a way that all the that there are only polynomials and not Laurent polynomials, and all the polynomials have constant term 0. So we want to write h as an element of the sum over all y, and then we take v times the polynomial ring times the basis element. Okay, so any such element is 0. So the element with these properties has to be 0. Once we have this, you can choose two potential candidates for the Kazhdan Lusztig basis element. You subtract one from the other, and the coefficient on hx is going to cancel out. The rest is going to be inside this sum here, and it's still going to be self-dual. So the difference between the two is 0, and the two candidates for the Kazhdan Lusztig basis element are the same. Okay. And this here is a nice little exercise, or if you're interested, you can also look it up in Zergel's paper. But yes, so essentially, this proof gives us an algorithm for computing the Kazhdan Lusztig basis and therefore the Kazhdan Lusztig polynomials, which I now want to go through in an example. I just want to sort of state this again for clarity. So we have.
Sorry, can I ask a question? So in this theorem, you basically show that the coefficients are integral. So can you say anything about the positivity of the coefficient?
It doesn't follow from this, I think.
Right.
This is an extremely hard problem,
Yes.
which I don't think there's any like purely combinatorial proof for it, unless you consider Zergel bimodules to be combinatorial.
Right. So that's a very deep fact of this.
Yes. So these polynomials will end up having non-negative coefficients, which in the case of when your W is a Weil group, you can actually get this from this result that I told you up here, because this tells you the coefficients of the Kazhdan Lusztig polynomials identify with the values of X group. I should have said earlier that this here is the true result of Bowman. And the result up there is due to Kashibara-Belinsky. And Violence and Bernstein independently. Okay. So I think there are proofs of the fact that the coefficients are positive in many different cases, but the only completely general proof that is available uses Zergel bimodules.
So the Kazhdan Lusztig paper came out in 1979.
Yes.
And I believe they proved this fairly shortly thereafter, maybe like 1980 or 81 or something.
80 or 81, I also think so. Yeah.
So,
and this uses geometric methods, so you can do this using D modules on flag varieties, for example. Okay.
good.
So now, just for the sake of completeness, so we write H underline X. Well, HY X times HY, and we call the base change coefficients between the Kazhdan Lusztig basis and the standard basis, the Kazhdan Lusztig polynomials. So this is a bit of a matter of convention. Some people would only define the Kazhdan Lusztig polynomials when y is less than x. But it's sort of nicer to have them available for every pair of elements of the Weil group, so you can just define them in general to be the base change coefficients. And the inverse Kazhdan Lusztig polynomials, which I mentioned up there in the introduction, are the inverse base change coefficients. So you get them by writing the standard basis element hy as a linear combination of the Kazhdan Lusztig basis, except you introduce a sign which depends on the length of y and x. So it's -1 to the length of y plus length of x. Then you get the inverse Kazhdan Lusztig polynomial yx, and then you get the Kazhdan Lusztig basis. And with this sign conventions, these polynomials are also going to have non-negative coefficients. That's why it's so convenient. The signs are a bit nasty in this formula, but they make the polynomials nicer. All right, let's do an example. Is this what you?
Yeah.
It's different than the other rooms. That's why I'm confused. And well, we do the smallest possible example. It is interesting, but I think in this example you already see everything that's going to be going on in the end. We look at the Y group of type A2, so the symmetric group on 3 points, which is generated by 2 reflections as T subject to relations S squared equals T squared equals 1 and ST STS equals TST. So this is going to have 6 elements: E, S, T, ST, TS, and STS. And what we're going to do is we're going to draw this in terms of its Kazhdan complex. So you can think of the symmetric group as sort of acting on these 3 lines, and it acts fully faithfully on the chambers again. So we can label them like E, S, T, ST, TS, STS, and then S acts by reflection through this line, T acts by reflection through this line, and if you start from E, you can sort of walk your way up to the highest chamber. And now what we already know is we have that H underline E is equal to HE, so we draw this in a picture as saying we have coefficient 1 down here, and we have coefficient 0 in all the other cells, so we would write it. Similarly, we can write H underline S is HS plus V. So we draw this in this picture where we put a 1 in the cell of S and a V in the cell of the identity, and the basis element corresponding to T looks the same except we reflect the image. So H T plus V, and the picture for this is 1 T cell and a V in the 1 cell. Now, basically what we want to do is we want to multiply H underline S. Okay, say we want to compute H underline ST, and we already know H underline S and H underline T. Then we start from this picture and we want to multiply from the right with H underline T, and we use our formulas that I wrote up here. Okay, so we walk through each non-zero coefficient in this decomposition, and we multiply the corresponding standard basis element with H underline T from the right. Okay, so this here is S, this here is identity. If we multiply S from the right with T, we end up with ST, which is above, right? So the picture that we get is basically the 1 that we had here produces a 1 here and a V here according to the upper one of the 2 formulas. If you take the identity, you multiply it with T, you just get T, which is also bigger than the identity. So starting from the V that we had down here, we're producing a V in this cell and a V squared in this cell. Now all the terms apart from the term on ST have constant term 0 in the polynomials. So this means that the product of these 2 is actually already the Kazhdan Lusztig basis element in this case. So this is H underline S times H underline T, and this is H ST plus V times HS plus V times HT plus V squared times HE, and you can compute the opposite one, so H underline TS exactly the same way. You get HTS plus V times HT plus V times HS plus V squared. Maybe we draw brackets here so you can see that these 2 things come from the same one underneath, and these 2 things come from the same underneath. Okay, and the picture. This is again the reflection of the picture we saw before. Now, in order to compute the last Kazhdan Lusztig basis element, the one corresponding to STS, we proceed in the same manner. So we start from h underline st, we multiply it with h underline s from the right. Okay. So what do we get? The 1 here in the st cell multiplied from the right with s produces sts, which is bigger than st. Okay. So now we get a 1 and a v. If we look at t and we multiply it with s from the right, then we're going to get ts, which is getting bigger. So we get a v in the ts cell and a v squared in the t cell. There's also something in biology, but anyways. So if you start from s, however, then you multiply with s from the right, you end up with the identity. So this is smaller. So now we're in the second case, and we get a factor of v inverse that we have to multiply with the v. So in the s cell, we get v times v inverse, which is 1. And in the 1 cell, we get v squared times v inverse, which is v. And then we get a contribution from the identity, which gives us v squared on the s cell and v cubed on the e cell. Okay, so we get 1 plus v squared and v plus v cubed. So this means the computation that I just made tells us that h underline st times h underline s is this picture. So it's h sts plus v times h st plus v times h ts plus v squared times ht plus 1 plus v squared times h s plus v cubed times he. And now we do exactly what the proof tells us to do. We subtract the Kazhdan Lusztig basis element corresponding to s, and we end up with the Kazhdan Lusztig basis element corresponding to sts. So this is just h underline st times h underline s minus h underline s, and we end up with the picture. We get 1 v on the 3 upper cells, then v squared on the right, and we remove the 1 from here, but we also have to remove the v from down here because that's what h underline s looks like. So this is sts plus v times hst plus v times hts plus v squared plus v cubed. So as you can see, this proof sort of gives us an algorithm for computing Kazhdan Lusztig polynomials that once you have an implementation of your Coxeter group in a computer, you can very easily implement this recursively, and it goes quite fast, I would say. Yeah, maybe I think I'll stop here. Nothing else to say. Are there any questions on Lusztig polynomials?
Sure. So, I mean, it is sort of stuff that you sort of alluded to, but there's this, you sort of identify the Heck algebra with like the Grothendieck ring of principal block of category O in this way that sends Verma modules to the standard basis and simples to the this Kazhdan Lusztig basis. But so then you have this kind of nice, purely Heck algebra way of characterizing the basis of simples. Are there other nice, like, kind of purely Heck algebra formulations of the bases corresponding to, say, like indecomposable projectives or indecomposable tiltings?
So I think in the category O case, all of this sort of ends up being either the standard basis or the Kazhdan Lusztig basis up to the correct identifications, because you have this kind of reciprocity that tells you that let me see. Sorry, what I'm saying is not quite correct. Let me start again. You have this characterization of the Kazhdan Lusztig basis, which says that the elements you're looking at should be self-dual, and the base change coefficients should be in V times that join B.
Mm-hmm.
Now you can define a sort of negative Kazhdan Lusztig basis, where again you ask that it's self-dual, but this time the base change coefficients would be in V inverse times Z V inverse. Okay, I mean the proof is exactly the same. But now, if I'm not mistaken, the negative Kazhdan Lusztig basis would correspond to projectives. Standard basis is Verma's, simple modules is Kazhdan Lusztig basis.
Oh, I see. And then what about tilting?
Tilting, so I'm not sure, but in the category O case, there's essentially this causal duality which interchanges the tilting module with the projectives. So it's a derived autoequivalence, but it sends certain sort of canonical modules to. Actually, let me see. I don't think you need causal duality. I think what you need is Ringel duality. So I'm getting a bit confused. I didn't look this up in detail before I gave the talk because I was talking about Kazhdan Lusztig polynomials in the category O. But so you have this Ringel duality functor which maps every projective module to a tilting module, and that sort of tells that the filtration multiplicity. Let me see what it'll tell you. So you can identify the Verma filtration multiplicities of tilting modules with composition multiplicities of Verma modules via Ringel duality. Or it's actually composition multiplicities of dual Verma modules, but these are the same as the composition multiplicities of the Verma modules. This follows from the fact due to Zergel, I think, that the principal block of category O is Ringel self-dual. So usually for every highest weight category you have a Ringel dual, and the standard filtration multiplicities in the tilting modules for the Ringel dual are the composition multiplicities for the co-standard modules in the original highest weight category. And since the principal block of category O is Ringel self-dual, you're going to get these multiplicities match up. And so in some way, like the multiplicities that you get are just the same, like Kazhdan Lusztig polynomials or inverse Kazhdan Lusztig polynomials evaluated at 1. And then basically it's a matter of sort of lining up your combinatorics correctly to see which basis should correspond to that.
Right. Yeah, I mean, that definitely makes sense. I was just kind of hoping if there was like a nice, this is such a nice description, like, okay, but evolution, and then you have the upper trend.
So what I was trying to say is you don't get a new kind of combinatorics from doing that.
It's just more Kazhdan Lusztig polynomials.
Yes, just sort of twist it around the right way somehow. Yeah.
A lot of this makes sense geometrically, like the I don't know, the HW is like a Schubert cell, and multiplication is like multiplying Schubert cells in the group. And then like with the bar, it's like the Schubert varieties. But
sure.
With like the H bar, it's like multiplying Schubert varieties in the group. But do you have like an interpretation for what inverse means? It's like mysterious.
Well, I guess you could try to understand it through the bar evolution, which this may be horribly wrong. I think this is Verdier duality. On the, I'm really not good at this, but I think this is Verdier duality on the category of purpose sheaves. And so this sort of tells you what the inverses are, at least on the standard basis. And I mean, inverting doesn't make sense everywhere. It only makes sense on the standard basis.
So you can take like the inverse of the Schubert cell. I'm wondering if you can interpret it like that.
I don't know. I mean, I think in a way, so the Werner modules sort of correspond to in your 6-functor formalism. There's like the proper push forward and the other one, right? And one of them corresponds to the Werner modules, and one of them corresponds to the dual Werner modules. And the homomorphism from the Werner module to the dual Werner modules comes from the two adjunctions. But so I'm not really sure if this inversion gives you something new. Like I think it's sort of just everything happening on the same set.
Other questions? Let's think, Jonathan.
Thank you.